So we have this example here where Anne is going bungee jumping. And after she jumps, the initial time, the rope stretches 120 feet. And then after each bounce, so imagine like someone bungee jumping, they go down and then they come back up. And then they go back down and they come back up. And it's kind of like that, you know, there's that bouncing effect going on, right?
No,
I know, it's terrifying. You guys know what I'm talking about, right? With the bungee jumping? Yes? Huh? Yeah? So the first time she jumps, the rope stretches 120 feet. And then she'll like snap back up and then she'll fall again. But each time she goes back down, each rebound, each bounce, please keep your phones away. The stretch is 60% of the previous bounce, of the previous rebound. So our recursive rules require two pieces, starting point and a rule to move from term to term. Our starting point here is 120 feet. Okay. And then our recursive rule is right in here. So we're saying the stretch is 60% of the previous jump. That means that we multiply the previous jump by 60%. How do we write 60% as a decimal? Yeah, 0.6. Yeah, right? We just have to move the decimal point over 2 places. 0.6. Okay. So our A0 will be 120, and our R will be 0.6. So at rebound 0, the stretch is 120 feet. After rebound 1, remember we need to multiply the previous term by the common ratio. So we do 120 times 0.6. And this is going to be equal to 72. So she bounces and the rope stretches 120 feet and then she kind of snaps back. And then she'll only go down 72 feet the next time. And then she'll snap back. And then after the second rebound, she's going to go 120 feet times 0.6. So that's like the previous jump, right? And then we again multiply it by 0.6. So this is equal to, comes up to 43.2. Can you read that? Should I write that somewhere else? Can you read it? Yeah, 43.2. Okay. And now our third jump, or the third rebound, we're going to take this previous jump, so 120 times 0.6 times 0.6 times 0.6 again, and this comes out to be 25.92. So let's think about each of these in a little bit of a different way. So when I have something like 3 times 3, what's another way I can write that with exponents? 3 to the power of 2, 3 squared. Or if I had 4 times 4 times 4, what would that equal? Yeah, 4 to the power of 3, 4 cubed. So the same thing's going to happen here. If I have 0.6 times 0.6 times 0.6, what's that going to equal? To the what power? Third. Yeah. So this one, after the third rebound, a simpler way to write our equation here is 120 times 120 times 0.6 cubed. For this one, it would have been 120 times 0.6 squared. This one, we only had one 0.6, was just 120 times 0.6 to the first. And then this one, the first one, still works. It's going to be 0.6 to the 0th power. Whenever we have anything to the 0th power, the 0.6 to the 0th power, always equals 1. 2 to the 0th power is 1. 4 to the 0th power is 1. Anything to the 0th power always equals 1. What do you notice about the exponent and the rebound number? The exponents and the rebound numbers. They're the same. Yeah, they're just counting up. Right. So if I asked you to tell me what the rebound would be for the 12th bounce, what would it be? Yeah. Don't forget our 120. It was 120 times 0.6 to the 12th, which comes out to be only 0.26. So after she's bounced back 12 times, at that 12th rebound, she'll only drop down like 3 inches. She's hardly moving anymore at all. Okay, and then what if I said, let's find the nth term, What would we do? So what's similar about the rebound number and our exponent? They're the same thing, right? How are they related? Yeah, they're the same. Just try to mess up. 3. So if I said I wanted to find the nth term, all I'd have to do is write 120 times 0.6 to the n. So now if I said, what about the 50th rebound or the 7th or whatever, we just plug that number in for n. Okay. Let's move on to these examples. Start with these two. Okay, so we want to extend these geometric sequences. So we want to first find the common ratio. And then let's find the next 3 terms in the sequence. So to find our common ratio, we need to look at how do we move from term to term? What do we need to multiply 1 by to get to 2? 2. Yeah, 1 times 2 is 2. What about the next part? 2 times what equals 4? 2. 2 equals 4. How about 4 to 8? 4 times what equals 8? Yeah. So what's our common multiplier, or common ratio? Equals 2. Yeah. And so what are our next three terms going to be? After 8. What's 8 times 2? 16. 16 times 2? 32. 32 times 2? Yeah, 64. There you go. All right, now this one's not quite so easy. 16 times what equals 20? 20 times what equals 25? 25 times what equals 31.25? So I'm going to show you a way to figure out what our ratio is, our common ratio. So I'm trying to figure out 16 times our common ratio R equals 20. How do I solve for R? What do I need to do? How do I solve for R? Not multiply 16. Yeah, you have to divide 16. So if I divide 16 by this side, I also divide this 16 by the other side. Now 16 cancels out. I'm left with R equals 20 over 16, which equals 1.25. Let's try the next one. So if I want to do 20 times R, that should equal 25. How do I solve for R? What do I need to do to solve for R? Yeah, divide by 20, divide by 20. So R equals, again, 1.25. So 16 times 1.25 gives me 20. 20 times 1.25 gives me 25. So what is my common ratio? What's my common ratio? Yeah, 1.25. 1.25. Okay, so now take 31.25, pull out your calculators, and I want you to find the next three terms. So we take what, 31.25, multiply by 1.25. What did you get for the next term? 31.25 times 1.25. Yeah, 39.0625. And then how about the next one? Just give it to me to 2 decimal places. $39.0625 times 1.25. Okay, one more. What do we get? Mm-hmm.